Right, ladies, today we are looking at the chemistry of water. And everything that you see here is purely for revision. So if I draw a Lewis diagram of water, you should be able to do something like this. You should be able to tell me that between oxygen and hydrogen, I've got a polar covalent bond and another one over there. You should also be able to tell me, because the oxygen end is slightly negative and the hydrogen end slightly positive, we have got a polar molecule. And because of the strong lone pair repulsion here and the weaker bonding pair repulsion over here, water has an angular shape. You should also be able to tell me that between water molecules, we have got hydrogen bonding forces, which are strong intermolecular forces. So water as a solid, ice in other words, these intermolecular forces are very strong. In liquid water, they are a bit weaker, and between the water molecules in a gas, the intermolecular forces are almost non-existent. Right, on page 91, they are doing something quite interesting over there, which I just wanted to show you. They try to calculate how many molecules we'll have in a liter of water, assuming that a liter of water has a mass of 1 kg. So over here, we use our mole formula, and number of moles equal to mass divided by molar mass. The 1 kg must be converted to grams, so we've got 1,000. And over here, I calculated the molar mass for water. Hydrogen has a mass of 1, another hydrogen atom, oxygen 16, which gave me a mass of 18 grams per mole, and I've got 55,56 moles. Then if I use the other mole formula, number of moles equal to the number of particles divided by Avogadro's number. So number of particles will be equal to my answer from there times 6,02 times 10 to the power of 23, which gives me 3,34 times 10 to the power of 25 molecules, which is a lot of water molecules. Okay, activity 4.6 on page 92. I would also like to take a look at that. So over there you've got a table with molecules, their boiling points as well as their mass, and you have to plot a graph. Now if you do that, the graph should end up looking something like this. Now let's look at those molecules. We've got H2O, we've got H2S, H2Se, H2Te. So what they've done, they have taken the elements that we find in group 6 and they have shown us what the molecules will look like if those elements bond with hydrogen. So hydrogen and oxygen gave me the water, hydrogen and sulfur gave me the H2S, and so on. So these molecules are known as hydrides because it's these atoms that have bonded with hydrogen. So if I look at the trend in this graph, I can see quite clearly that it seems like water doesn't fit in at all. If I follow the trend over here, it looks like water should have a boiling point of approximately negative 80 degrees Celsius maybe. And that is definitely not the case because we know that water has a boiling point of 100 degrees Celsius. So what is the reason for this? And that's the answer to question 4, which I did first. And the answer is hydrogen bonding forces. Because these bonding forces are so strong, we find that a lot of energy is needed to separate the molecules in the liquid phase to change into the gaseous phase, and that is why water has such a high boiling point compared to the other molecules that we've got over there. And then the other thing that you must see over here, if we take a look at these 3 molecules over here, so why the difference in boiling point over here, where H2Te has the highest boiling point, and what comes in here is the relative size of the molecules. So even if they've got similar intermolecular forces, the largest molecule will experience the stronger intermolecular forces between the molecules. So that is actually the answer to number 3. The strength of intermolecular forces increase as molecular size increases. Okay, and then just the last couple of things that we have to look at when we talk about the chemistry of water. And something quite interesting is that if it wasn't for hydrogen bonding forces, all water present on Earth would have been in the gaseous phase. So that means we would not have any liquid water on the surface of the Earth, so no rivers, no lakes, no oceans, and so on. And the second interesting thing about water is the fact that solid water is less dense than liquid water. And you've all seen ice cubes float in water. Now, what is the reason for this? And there are two things, and that is the angular shape of the water molecule and the strong hydrogen bonding forces pulling the molecules together. This actually causes them to arrange themselves in a three-dimensional hexagonal lattice with spaces in the centers between the molecules. In your textbook, on page 95, they talk about the tetrahedral arrangement, which you can take a look at as well. And because of this specific arrangement, solid water is actually less dense than liquid water. And this ensures the survival of aquatic life in cold areas, because what happens is in a river, when it gets very cold and the water starts to freeze, a layer of ice will form on the surface of the river, for example, and the aquatic life can still survive in the river because the layer is going to be on the river and it doesn't sink in to the bottom of the river, so that the river ices from the bottom upwards. So that doesn't happen, and this, as we've already said, ensures the survival of aquatic life in cold areas. And then lastly, because these hydrogen bonding forces are so strong, a lot of energy is required to separate water molecules so that they move from a liquid to a gas. So this means that water can absorb a lot of energy before the water temperature rises, and therefore before it is able to change from a liquid to a gas. For this reason, we say that water has a high heat of vaporization. And this is also very important because this means that the sea and other large bodies of water act as heat reservoirs that regulate temperature fluctuations, and in this way they actually help to moderate the climate that we have here on Earth. So hopefully, as you can see, the unique chemistry of water makes life on Earth possible. And what you can do for me now is on page 98, there are some questions that you can go answer. The answers to those questions I will post maybe on Tuesday after the long weekend. There is also an exam practice on page 100 to page 102. This you can do in your own time, and what we can then maybe do once we're back at school, we can go through those answers as part of our revision. So this I will post the answers for, as I said, but this you can do in your own time so long, but we'll discuss them once we are back at school. Thank you, ladies.